Okay, so for the redox section, the next part is electrode potentials. And the special note before I start is when writing redox half equations, we should write them as reductions. So, a half cell is a metal which is dipped in its salt solution. If the half cell, however, consists of two aqueous ions, we use a platinum electrode. We use platinum because it's inert, so it won't react with any of the substances, and it conducts electricity, which is pretty important for a cell. An electrochemical cell then is made up by two half cells, and these are connected by a wire and a salt bridge. The wire allows electrons to flow through it. The salt bridge completes the circuit by allowing ions to flow through it. At each half cell, a redox reaction occurs. The half cell which is oxidized goes to the left of the cell, and this one is known as the reducing agent. We can determine the reducing agent using the electrode potentials, and this is because electrode potentials are a measure of how easily a metal loses its electrons. So, a better reducing agent will have a more negative electrode potential. So, creating a cell diagram. First, we need to decide what the reducing agent is by using cell potentials. Well, the more negative electrode potential will be the reducing agent. So, what we do with this is we flip it and then we write it as an oxidation. Then, we will write this on the left hand side and we'll have the reduction on the right hand side. As I discussed here, the cell which is oxidized goes to the left. So, once we've done this and we've got our two half equations, we basically have to write it in this order for the cell diagram. We write it as a reactant of the oxidation, and then we use this little sign here which represents a phase change. Then we do the product of the oxidation. Now we use this symbol which represents the salt bridge. Then we do the reactant of the reduction, and we could here have used a comma which would have represented the same phase, if of course it was the same phase, and then finally the product of the reduction. And just a random trend you'll notice is the charges will kind of go up in the middle, but the ends will be the lowest. It'll make sense when you see one. So, the positive electrode in a cell is where the oxidation occurs, and this is to the left. The negative electrode is where the reduction occurs, and this is to the right of the cell. Finally, to calculate the overall cell potential, we use the formula of E cell is equal to the E right minus E left. And that's meaning the electrode potential of the right side, the reduction, take away the left side, the oxidation. And that's it for redox electrode potentials. As you can see, I nicely blocked them out because we've done them now.